Okay, it's almost spring break. You got the assignment due coming up. Any questions or problems about that before we go on? Yes?
Do you have any tips on how to solve if 7 3, which is one of the A to B to C mod and against the algorithm?
Well, okay, so imagine you were on a circular track that was a mile around. And you start here. Now let's make it 10 miles around. And you're on a bicycle. And someone says you've got to ride that many miles around, some massive number. Where would you end up? It's 10 miles around. You start here, you're riding in this direction. You go that many miles. Where would you end up? Yeah? Yeah, right back at your start. How did you do that? How did you calculate that huge number so fast?
Just because we know that it's raised to 10, like a power of 10.
Right. So he looked at that and knew that's a power 10, so that's going to be an even number of times. Basically, he did a mod in his head. Okay? Now, what if it were this? What if it were 3 plus that? Where would you end up? You'd end up at the 3 mile mark over here somewhere. Okay? That's another mod. Basically, you took the mod 10 of that really fast and figured it out. So you're dealing with a giant exponent, sort of like that. Okay? Now, if you think of the problem as this, that you've got to find a quick way to compute A to the B to the C mod n, if that's how you describe the problem to people, you're not going to be able to do it. Okay? What am I leaving out here? Set?
A to the K, like we were given A to the K.
Right. You know that the inverse of A mod n is A to the K minus 1. You've got to use that fact. Basically, use this fact to figure out how big around the track is. Now, you can chew on that. That's my hint.
How do we word? That's the problem I'm getting stuck at, is just wording it. How do we word, like, write the solution, like write the algorithm? It's like,
Well, the correct solution will be you do this and then you do this.
okay.
Yeah. Where this is a simple thing. So what does it mean when we say that A and A to the K minus 1 are inverses? Yeah?
It means that A times A K minus 1 is convenient to 1 mod n.
Right. We know that A to the K is equal to 1 mod n. So go with that. Okay, so I'm going to make a deal with you. I will extend the deadline on the assignment if you will understand when I don't look at Piazza for a week. I'm not going to extend it indefinitely. I'll extend it like 2 days. Would that be helpful?
Yes.
Okay, I don't want to. If I extend it by a week, I'd ruin your spring break. But, okay, so I'll extend it deadlines by two, and
Is that for this one or the
for this one. Yeah. PS8 will come out probably tomorrow, but it won't be due for 2 weeks. So. Okay, any other questions? Yeah?
On quiz 1, question 3, do you have it or should I say it?
Better say it.
Let 0 be less than A, be less than B, be less than N,
Mm-hmm.
less than C. And if A to the B is equivalent to 1 mod N,
Mm-hmm.
which of the following is always equivalent to A to the C mod N? And then it gives you 4 different things to choose from.
Mm-hmm.
Just talking to some other people about that, and I can't find a way to do that without just throwing a ton of numbers at it.
Yeah, I'm not exactly sure how to give a hint on a multiple choice question like that. I'd be happy to talk to people individually about it. But essentially, you've got to, try to prove that, using this fact here, using A to the B is 1 mod N, use that to simplify each thing and see where you go. Sorry, I can't be more helpful there. Any other questions? Okay. So we've been talking about the RSA algorithm and in general about encryption. And just to remind you, again, how it works. You start with 2 distinct primes, P and Q. You form their product, and that's called the modulus, N. So N is the product of 2 prime numbers. Now, where do the prime numbers come from? They need to be, for real use, they need to be 1,024 bits each. So where do you find a 1,024-bit prime number? Yeah?
Isn't it just the probability testing thing? Is that for mod?
Sure, it's probability testing, but what do you test with the probability tester? So yeah?
You can multiply 2 very large primes and add 1. And that would be 1.
Well, he said you could multiply 2 very large primes and add 1. That won't necessarily get you a prime number, though. Not necessarily. Like 3 times 5 is 15. Add 1, you get 16. That's not prime. So where do I get a 1,024-bit prime number? Okay, so let's think about it. We need to choose at random 2 large prime numbers, and we know how to efficiently test whether a number is prime. Yeah?
Just kind of brute force it and start looking at a bunch of 1,024-bit odd numbers.
Okay. So you just use a random number generator. It needs to be a good random number generator. The ones you're used to using are pseudo-random number generators. If you know the seed that was used, then it's completely deterministic. So it's actually anything but random. It's good enough for most purposes. It's not good enough for encryption. So they're cryptographically secure random number generators. So you just generate 1,024 random bits. Or as he suggested, 1,023 random bits and put a 1 on the end because the number needs to be odd. And then test it. See if it's random. And just keep generating random ones until you get one, until you get 2 that are prime. So anyway, you multiply those 2, you compute phi, that's easy. You look for E, look for a small e that has the GCD property with phi, and then you find E's inverse. And now you've got your RSA key. To encrypt, we raise the message to the power D mod n, do it mod n. I'm sorry, to the power E and do it mod n. Then decrypt, you raise to the power D mod n. And we saw that if you do that, that's called encryption. If you go in the opposite direction, if you encrypt with D and decrypt with E, that's called signing and verification. That's used for authentication. And I told you I'd show you how it all fit together. So here's the proof. I'm not going to go over the proof again. But I want to talk about some vulnerabilities of the algorithm. So the obvious way, as I mentioned, to attack RSA is to take that modulus in and factor it. Because the public key is the combination of D and of E and N, the exponent, the public exponent, and the modulus. So they're both. We assume everyone knows what they are. The private key is the combination of D and N, and D is the only secret part there because N's in both places. And it is believed that there's no better way to attack RSA than by trying to factor. So people have tried to factor. RSA Labs put out a challenge years ago. They created a series of increasingly long RSA moduli and put them up and challenged the community to factor them and offered cash prizes for a while. They finally withdrew the cash prizes. But the numbers are still up there. And the longest one that's ever been factored was RSA 768. So it's a 768-bit modulus. And we've abandoned 1024-bit moduli in favor of 2048-bit moduli. So that's to date the largest RSA modulus ever factored. It was done in 2009, so about 10 years ago it was factored. And they had better algorithms than any of us are likely to use. They didn't just do divide and check. People have studied factoring a lot, and even though no good way is known to factor, some ways are better than others. It involved a team of researchers from all those countries. Step 1 took 6 months on 80 processors. That was the pre-processing step. Step 2 took 2 years on hundreds of machines, and they estimated on a single core 2 gigahertz processor it would have taken 1,500 years. So a lot of computer time. And they factored it, and then they predicted that by the year 2020, which is just next year, that a 1024-bit number would be factorable. And that was part of the impetus to abandon moduli at that length and go to longer ones. So anyway, it takes a great deal of effort. You can see that to factor just 232-digit number. Now let me show you another vulnerability. So in 2012, some researchers in Switzerland went out on the web and found all the RSA public keys that they could, because they're public. So they found 7.1 million public keys out there. There's probably more, but that's just the ones they worked on. And they found that 27,000 of them offered no security at all. They were useless. Let me explain why. The problem is they found pairs of keys. They didn't find pairs of keys that were using the same modulus, but they found pairs of keys that were whose moduli shared a factor. Okay, so they found a modulus N1 and a modulus N2, and it turned out that they had a factor in common. So let's think about how that would help you attack it. Suppose N1 is the product of P and Q1, 2 prime numbers, and N2 happens to be the factor of P and Q2. So they share this factor P. N1 and N2 are different, but they share that P. In that case, it's easy to factor the number. You just compute the GCD of the 2 moduli, and you get out P. And then you divide by P, you've got the Q's. So by themselves, each individual modulus, each individual key was secure. It was just the fact that there's one over here and one over here, and the 2 share a factor. Yeah.
How long would it take to actually realize that two moduli share a factor, assuming that you're going through, I would guess, thousands of keys?
Well, they went through 7.1 million. When you're generating the key, you don't have any way of knowing if anyone has ever used one of those same prime numbers or not. But they were able to do it quickly because GCD is fast. They just did a pairwise GCD on all 7.1 million keys, compared each key to the other using GCD. And they found 27,000 of them shared a prime factor. So how does that happen? How do 2 key generating programs working independently produce that many keys that share a prime number. Yeah,
You have a good enough random number.
right. It's a bad random number generator. So, you know, it may, I don't know if it was, if these keys came from the same software that generated them, but they weren't random. So the security of RSA depends on the prime. You want to generate a prime that no one has generated before. Because if someone has generated it and used it in an RSA key, then you're vulnerable. So you really got to have a good random number generator. Now, what's the odds? If you have a truly good random number generator that's essentially flipping a coin for each bit, what's the odds that two identical 1024-bit prime numbers are going to be generated independently? 1 chance in 2 to the 1024. It certainly ain't going to happen 27,000 times out of 7.1 million tries. It's not going to happen at all in 7.1 million tries. So that was an implementation mistake that led to that vulnerability. It seemed to be, it was limited to embedded devices like routers and VPN devices and such. So it wasn't on big servers. Yeah?
How inefficient would be an attack that did a random number generator less than n and just did GCD that number with n to find a key?
Yeah, well actually you would, well what you're describing is an approach to factoring. You're basically saying guess the factor and divide it or do GCD and see if it is a factor. You know, it would, there are just too many, the keys are too long that there are just too many to try. Assuming good random number generation, you have to be able to, you need a good factoring algorithm to do this. Now, no one's found a good factoring algorithm except on quantum computers. There are quantum algorithms that can do fast factoring. So if they ever succeed in building an operating real quantum computer, they already know how to program it to defeat RSA. So RSA's time will come for one reason or another. Either someone will figure out factoring or quantum computers will be built, or it'll just become too slow because the keys get too long. And there's a backup plan. There's another way to do public key encryption. It's just that could be rolled out when it's needed. Yeah.
Part of the reason why it's limited to embedded devices is because embedded devices often don't have a good source of randomness. Like,
Well, the keys were on embedded devices, but that doesn't mean the keys were generated there. I'm not sure if they were generated there or not. So yeah, I don't really have any more insight than that. Okay, so those are just a couple of vulnerabilities that have cropped up. Now, I want to finish this discussion of encryption by talking about electronic commerce. So let's we're going to go through a few thought experiments. So what we have on the left is A. You can think of A as Amazon, and on the right is B. You can think of that as your browser. And we're going to try to buy something from Amazon. So here's the first try. Your browser generates an AES key. So an AES key is 256 random bits. And it's often called a session key. So typically one would be generated and used for the duration of a secure session and discarded. So your browser generates a random AES key and sends it to Amazon. Amazon then has to send you a message. They encrypt it using K, and you can decrypt it on your end because you've got K. And when you send them your credit card number, it can be encrypted by your browser, and Amazon can decrypt it. So that's what electronic commerce would look like if we just used symmetric AES. What's the problem? We've already talked about the problem with this. Yeah.
someone can grab K and just go.
Right, someone could grab K in the middle. So there's Eve in the middle. So these kinds of scenarios you'll often see called man-in-the-middle attacks. There's someone in the middle that's sort of invisible to either party, intercepting the communication and manipulating the communications sometimes, such that neither A nor B knows what's going on, but he's hiding out in the middle. So let's see what that would look like with Eve in the middle. Browser sends the key to Amazon, but Eve intercepts it and remembers it and just sends it on to Amazon. So it looks good to Amazon. It got the key it was expecting. And then when the encrypted message comes back, Eve intercepts, decrypts the message, and sends the encrypted message onto the browser, and so on in reverse. So Eve is able to read everything that goes by. Just has to be able to tap in somewhere in the middle. Okay? So that's why that doesn't work. That makes sense? Okay. So the vulnerability of AES is key transfer, like we just saw. The problem with RSA solves that problem. You don't have to do a key transfer. RSA, though, is too slow to use exclusively. You've got that end of the third encryption exponentiation step to do. So what sounds like a good compromise to use? If you've got one algorithm that's expensive but doesn't involve a key transfer problem, and another algorithm that's efficient but does have the problem, what do you do?
Do RSA first and then use AES to send messages back and forth.
So the idea is to use RSA to send the AES key. And then when the AES key is on both sides, then you communicate using AES. So let's see how that would work. So Amazon sends its public key to the browser. It says, here, use this public key to encrypt messages. So the browser generates an AES key and encrypts it using Amazon's public key and sends it to Amazon. Now Amazon can decrypt with its secret key, and now it knows K, and then they can communicate as before. So the AES, the RSA is just used for that first step of transmitting the AES public key. And then you've got the quicker AES encryption to do the bulk communication. Okay, so that's the idea. It's not how it's done because there's an attack, but that's sort of our first step toward the idea.
Wait,
Yeah.
you said there's an attack?
There's a way to attack this, yes.
Will we go over that?
Yeah, we'll go over that. Okay? So what could Eve do if we put her in the middle? Yeah?
Could she ask Amazon for their public key and try and encrypt it with like something else to try and see what it changes to?
Okay. So yeah, she could intercept the public key. We assume Eve knows the public key. Or she can intercept it when the browser asks for it. But what can she do with that? The RSA is designed to be secure. Yeah?
Intercept the messages that were sent with the AES key.
Well, suppose she intercepts this message coming back with the AES key. Can she decrypt it?
No.
She doesn't have Amazon's secret key. Yeah?
Could she send her own AES key instead of sending B's?
Well, how could she send? Well, let's see. She could intercept this message coming through, and then she could throw it away, and then generate her own AES key, and encrypt it and send it to Amazon. And now Amazon thinks it's received the key from Eve. Okay. What would happen when Amazon encrypted that message?
We wouldn't receive the same information.
Wouldn't receive what?
The same information.
Same information as what?
Assuming that maybe the key contains information like the person's name or credit card or
Well, the key is just 256 bits. So
okay.
key K is 256 bits. So yeah. So now Amazon decrypts it, gets the key, and then tries to communicate with B. Well, Eve can intercept that, but now Eve is talking to Amazon. Is Eve ever see? But she can't see anything that.
Oh yeah, B can't receive message 1
Yeah.
because
Yeah. B. Okay, once Eve has intercepted it and substituted her own AES key, B will never be able to decrypt it because B doesn't know that key. So yeah, she can sit in the middle and pretend to be the browser and order things, but she'll have to pay for it with her own credit card number. She wants to intercept the one coming from B, but B can't communicate in the conversation anymore because it's not using the AES key that Amazon is. Yeah.
No. Alright, so yes, Eve could intercept the very first message, then kind of make up their own public key
Okay.
and pass on to B.
Alright. That's the attack. Is she's going to intercept Amazon's public key and substitute her own public key. So just to be clear, this thing we've just been discussing is the public key goes to B unscathed. B uses it to generate this key K, and then Amazon
They can decrypt it.
Eve throws it away and substitutes her own key. But now B is sort of out of the loop. So this is the classical man-in-the-middle attack. Amazon sends its public key to E. Eve remembers it and sends her public key to B. It's all the same to B. It's just a modulus and an exponent. All the keys look the same. So B generates that key K and sends it to Eve. Now what's Eve going to do? She sends it to Amazon, but Eve intercepts it. Now what's Eve going to do?
Decrypted and send the same information encrypted by.
Okay, so Eve can decrypt it because she knows her secret key, so she'll recover K and then re-encrypt it with Amazon's public key, which she's holding. And that's exactly what Amazon was expecting to receive, is a key encrypted with a public key. Okay, so we decrypt on this end, and now we're communicating back and forth. But in between, Eve can read everything because she knows the key K. So she's sitting in the middle. She was able to, B thinks it's talking to Amazon. Amazon thinks it's talking to the browser, but really they're both talking to Eve. So that's a problem. Now, what's the root problem here? Yeah.
Eve is able to get into the middle.
Well, Eve is able to get into the middle, and we're going to assume that's possible. We don't really control the whole network. Yeah?
B doesn't know who's talking to it.
Right. B's got no way of knowing who he's talking to. So there's encryption here, but there's no authentication. Okay? We somehow, basically, Bob asked Amazon for the public key of Amazon, and Bob got a public key back. But it's not Amazon's public key, and Bob's got no way to know that. Yeah?
Could Amazon sign that public key?
Exactly. This is where the signature part of RSA comes in. So remember, to sign something, you encrypt it with your secret key, and then you encrypt it with a secret key, and then it can only be decrypted with the corresponding public key. But then you know that if you know whose public key it was, you know who's signed it. So let me show you how this works. So there are third parties, certifying authorities, like VeriSign, for example, you may have heard of. And they're in the business of signing public keys. So what Amazon does, if they want to do e-commerce, is they generate a public key and a private key pair, and they go to VeriSign and they say, hello VeriSign, we are Amazon, this is our address, this is our IP address, I guess. So this is our name, this is our IP address, this is our public key. And what VeriSign does is put it all in a document called a certificate, digital document called a certificate, because it's identifying information about Amazon, and they sign it with their secret key. So S sub C there stands for the certifying authority, or VeriSign. So they encrypt it with their secret key, and then they give it back to Amazon. Amazon pays them whatever. And now, when B doesn't ask for Amazon's public key, B asks for Amazon's certificate, signed certificate. So what comes across is the signed certificate, S sub C. Now, what's the browser going to do with that?
It can't decrypt it.
Well, it needs to know it's the public key and verification.
Right. So basically, Amazon, here is a certificate that is signed by VeriSign. So what's the browser going to have to do when it receives a signed certificate? Yeah.
Checks with VeriSign.
Well, it's right. It's basically it's going to take VeriSign's public key and try to decrypt the signed message. And if it gets back a valid certificate, the decryption succeeded, and the certificate must have been originally signed by VeriSign. Otherwise, it wouldn't have verified. Yeah.
So why couldn't a company just create an identical document
Another company could create a identical document, but they couldn't sign it with VeriSign's secret key because they don't know it. Right? Yeah?
So this is assuming that browser is then going to communicate with VeriSign to check and make sure that this is
Okay.
Yes.
So yeah, the question is, where does that public key for VeriSign come from? We'll get to that in a minute. Okay? But for right now, just assume that the sign certificate comes over. It's just a bunch of bits, presumably that was encrypted using VeriSign's secret key. In other words, it was signed. And the browser's job is to take the known public key of VeriSign or their similar companies and decrypt that message. And if it gets back something that looks like certificate, then it's valid. It was signed by VeriSign because only they could have signed it. So that's how the public key gets to be. Then we decrypt with VeriSign's public key, and then we're back doing what we did before. Okay, now the question is, where does the public key come from? Because what would happen if browser turned around and communicated with VeriSign and says, please send me your public key?
Then Eve could just go between browser.
Right, Eve could intercept that and send back, her public key. So what Eve could do is sit in the middle. When this signed certificate comes over, she could just throw it away. Or not throw it away, she could decrypt it. Because it's just signed by VeriSign, she knows VeriSign's public key. And then send it along. And then when browser asks VeriSign for its public key, Eve could intercept that message, send her public key instead. So I said that wrong. She would intercept the certificate, decrypt it, and then do what? Re-sign it with her private key and send it on. And then when the browser asks for VeriSign's public key, she would send hers. And she can read everything that's going on.
So that's why Amazon doesn't just sign with their own private key.
Right, if Amazon signs with its private key, where would we go get Amazon's private key? Public key to verify it. But where do we get, how does the browser get VeriSign's public key? You think of a way to solve that problem? Yeah.
Could it come pre-installed?
Yes. It comes installed in the browser. So one solution would be to use e-commerce, everyone has to put their public key into your browser. Right, and that would be a nightmare because of thousands or millions of e-commerce companies. So instead, your browser comes pre-installed with a few trusted root certificates. So it's just built in. VeriSign has various public keys that are built into your browser that can be used to verify certificates that come over. So when you use a browser, you are trusting that they only use reputable signing authorities, certifying authorities. They only put reputable keys into your browser. Yeah.
So would this hypothetical be possible that could someone go over to browser give it a hidden download, like viruses do, give it self-authority as a certificate, and then read between A and B.
Right. So if you could hack a browser by adding your certificate as one of the trusted root certificates to a browser, then you could start playing games. Now, where do browsers come from? How'd you get Chrome on your computer? A lot of you probably downloaded your browser. How do you know you didn't download it from Eve? Eve could be in the middle of the download of the browser and be give you a version that has her root certificate in there. Yeah.
So like checksums where they hash the download for the browser.
Okay.
And then they post the hash online.
That's right. So when you download the browser, it'll say on the web page, this is the checksum. So you run a hash algorithm on the binary of the browser, you should get this hash. And in theory, when you download, you can check the hash. And probably installers would do that. But yeah.
So if a browser had some kind of exploit and somebody they could get in and change those keys
Right.
So
That's an obvious way to hack a browser.
So it just seems like it gets more and more convoluted every step you take to make
Yeah.
sure it's secure.
Yeah, it's a difficult topic. So this is a root certificate that I pulled out of my browser some years ago. This one was issued in 1997 and expired in 2016. So you can see, and this is just what the browser shows to me. it was VeriSign right there. And here is the actual modulus. So that's the public key for that VeriSign public key pair. And there's the text code. And if this could be factored, then you could again play tricks. You could pretend to be VeriSign. Why does it have an expiration date? Why would a giant modulus expire? Yeah.
Isn't that like what you mentioned earlier? They expect people to be able to factor over that course of time.
Right. So one reason is it expires because you assume that people get better at factoring, and so we don't want to be using it after this date because it's going to be too short by that date. That's sort of the technical reason. There's a more cynical reason. Yeah.
Same reason we change our passwords. We don't want if one person somehow gets it, we don't want to keep using it.
Yeah, that's true. This is you know, if I have an RSA key pair and you crack it, you can crack me. If you can crack VeriSign's public key, you can factor that thing right there, and you can attack everybody. So that's a high value target. Okay. There's another reason. Yeah.
VeriSign wants to keep making money.
Yeah, VeriSign wants to keep making money. So actually, I guess a better example of that would be when I buy a certificate from Amazon, from VeriSign. It doesn't last, 9 years. It lasts maybe 2 years or 1 year. I have to keep paying them more money to get it, to renew it. So that's how they make money. Yeah.
It's almost 2048 now.
Yeah. Nowadays, right. So nowadays it's 2048 anyway. That's expired 3 years ago. Okay. So that's the deal with e-commerce. It could all come crashing down with no notice if someone discovers a fast factoring algorithm. Yeah.
This was just a fun tidbit that I read. Chrome has a zero-day exploit that came out last week that allows websites to alter files on your browser. And I didn't realize how big of a deal it was, but if you're talking about root certificates and if websites can alter the root certificates through this exploit, then that's probably a really bad thing.
Yes. Yeah. Being able to alter root certificates is a very bad thing. Yeah.
So the key is that Eve doesn't have VeriSign's public key.
Eve has VeriSign's public key. Because Eve can, the public key is public. What makes it secure is that Eve can't substitute her own public key and sign it as VeriSign. She can't authenticate something she generates as VeriSign. But she doesn't know VeriSign's secret key. So it was the authentication piece that sort of closed the loop here. VeriSign's able to prove they are who they say they are, that they're the ones that sign the certificate because you trust that you have their public key because it's sitting in your browser. Like that. And it only will work with their secret key, which only they know. Okay? Any other questions? Yeah?
So is this public key going to be the same across all browsers? And how does Amazon know?
Yeah, it'd be the same certificate across browsers. Right? This was in my browser, it would have been in everyone's browser. Whenever I pulled it out, I don't remember.
So if someone was able to figure out just that.
Oh, sure.
key,
Right. So forget about cracking RSA 1024 and becoming famous. You crack this one, if you're a criminal, you could become rich. Or you could end up in prison. Yeah.
Does VeriSign give their secret key to the company?
No. VeriSign takes the information that goes into a certificate, which is the name of the company, the IP address of the company, the public key, and signs it for them.
So the company comes to them with their public key and says,
Right.
sign this for me.
Right. And VeriSign, I guess they're supposed to verify somehow that they're talking to I'm not sure exactly how VeriSign does its business, but presumably they do it in a trustworthy way. All right, let's take a break and we'll look at a new topic. All right, so now we move to chapter 5, I think it is, which is greedy algorithms. So let's start with an example of a problem you can solve with a greedy algorithm. So you're given a list of possible meetings. So the idea is, this black line down here is a room. You can think of this, think of it as time. So maybe this is 9 a.m. to 5 a.m. And we want to fit meetings into this room. And these white lines represent the duration of meetings. So this meeting at the top, maybe it goes from 10 to 1:30. And this one over here goes from 4:30 to 5 or something like that. And you want to schedule as many meetings as possible. That's our goal. Schedule as many meetings as possible, in the room. What's the answer in this case? Yeah. 4. So let's see, I think I can actually animate it. So to do 4, you would do those 4. So those 4 all fit in the room sequentially. And we can have 2 meetings at the same time. If, for example, we pick this long meeting first, then you get 2 more, but that's all. So you can get 4 meetings. So that's our problem. We got a room, a bunch of meetings. We want to maximize the number of meetings we can put in the room. So can you think how to do it? Yeah?
I think naively you would start with like whatever the first meeting time is and kind of put that as the first.
Okay, so you take the meeting that starts first. Well, let's see if we did that here. What if we took this meeting? This is the one that starts first, so we'll do this one, put that in the room. Now we've got to figure out how to optimize the rest of the time. Okay, what's the best we're able to do if we do that?
The next available meeting.
This would be the next available meeting. And this would be the next available meeting. That's just 3. Yeah.
I mean, the brute force approach is you just try every permutation.
Okay. The brute force approach is to try every permutation. But in general, that becomes, if they're n meetings, there's 2 to the n subset to worry about. If the n's large, that's not going to fly. So the idea behind a greedy algorithm, so there are algorithms that try all the possibilities. There are algorithms that try some possibility and realize it made a mistake and back it up and try a different one. The hallmark of a greedy algorithm is it finds a way to just look at all the possibilities and make the right choice. Make a choice that's not going to lead to a dead end. So without ever having to back up. We won't be able to go, we need to be able to look at this and say, yes, this is obviously the one I'm going to put in there first. And then you look at the rest and say, that's the best to put in next. In a way that each choice, if you make each choice according to some rule, you're guaranteed to get an optimal solution. So greedy algorithms are used when we need to optimize something. And we're very happy we can find greedy algorithms because they're particularly efficient, because there's no trying and failing and backing up and trying again. Yeah?
Couldn't you just look for the earliest one?
Okay, he said look at the earliest end time. So in fact, that's how these were generated. Which of these meetings ends first?
The first highlight.
This one ends first. Then we have to rule these 2 out because they conflict. For the meetings that are left, which one ends first?
The second.
This one. Now we got to rule this one out because there's a conflict. This one ends first. That one ends first. Among the ones that are left. So that's called the greedy choice. So when you design a greedy algorithm, you've got to find a way to efficiently make the greedy choice. And that greedy choice has got to have the property that it can lead to a solution. It can lead to an optimal solution. It's not going to lead to a dead end where you get a suboptimal solution and have to back up and try again. And they can be hard to come up with. It's interesting that, so greedy algorithms are typically more efficient than backtracking algorithms. The backtracking ones are easier to write because you just try all the possibilities. That's just a pile of looping and recursion and you figure out the best solution. This requires some cleverness. And it's probably not obvious at all. You ought to look at the earliest ending time. Okay, so that's what I'm saying. Pick the meeting with the earliest ending time, discard all conflicting meetings, and then repeat until there's no left to schedule. So that's what we did. That's the earliest ending time. We throw away the conflicting ones. That's the earliest ending time. We throw away. That's the earliest ending time. That's the earliest ending time. So that's our algorithm. Now, right now, you're just trusting me that it works, or maybe you don't believe that it works. So we need some sort of argument to suggest that this greedy choice works, and we'll get to that. Okay, here's some other ideas. What about picking the shortest meeting first? So now you can imagine any set of meetings that you want. Can you think of a counterexample that would show that picking the shortest meeting first will fail sometimes? Yeah.
Well, the first shortest meeting would probably be farther down the line, and you have something already here towards the beginning of the timeline.
Okay. Can you give me like a concrete picture to draw?
2 long meetings directly after each other, but then 1 short meeting overlapping them.
Yep. So we have 3 candidate meetings. This is the shortest meeting. But if we kick it as our greedy choice, that's all we're going to be able to do. It's going to rule out both of those conflicting meetings. So that's an example of a greedy choice that you might think won't work, and you come up with a counterexample that shows it doesn't. What about this? I guess we already did the earliest starting time first. So there's an example. Earliest starting time, maybe there's a meeting that lasts all day. It starts first, but there could be 100 meetings you could schedule if they're really short. Now, you might be looking at this and saying, well, this makes better use of the room. Right? But that's just a different problem. If your goal is to minimize the amount of time the room isn't being used, that's a different problem. So that would take a different solution. We're trying to make committee chairs happy as opposed to people that build conference rooms. Now, this is one that comes up. Pick the meeting with the fewest conflicts first. So maybe if you have a meeting that doesn't conflict with any other meetings, clearly you want to pick it, right? Because it's not going to rule anything else out. Does that extend? Hard to come up with a counterexample, but it is possible. Yeah.
What if you have one really long meeting and it overlaps with another one, and underneath that you have a bunch of other meetings that are really tiny?
Okay. So it's interesting how these descriptions sort of describe what's going on. So here's the simplest example drawing I was able to come up with. So we're trying to pick the meeting with the fewest conflicts first. So which meeting is that?
The middle, the bottom.
This one has the fewest conflicts. It only conflicts with two meetings. But if you pick this one, what's the best you can do?
3.
Yeah, you can pick. You can run one meeting on this side and one meeting on that side and get 3. On the other hand, there's that. So that's one way you could approach deciding that a greedy choice, a way of making greedy choices correct. If you don't feel like proving it's correct, you could just try to prove it's incorrect. Try to find a counterexample, and if you think long enough and you don't find a counterexample, then you assume it's true. I had a math class in college where the tests were take-home tests that consisted of 10 true-false questions. And that sounds like it'd be easy, except each question was like, is this a theorem? And so my approach was I spent the time for the exam just trying to find counterexamples. And if I did, I said it was false, it wasn't a theorem, and otherwise I said it was true. And that worked out pretty well. I didn't get them all right, but I got a lot right. But we'd like to be able to prove these things are correct. So let's try to construct a proof that the greedy choice that I say is correct is correct. So the idea is we need to show that there is going to be an optimal solution that contains the meeting at the earliest ending time. We want to show that it's safe to make that first choice. We want to show that if we choose the greedy choice first, there's a way to get from there to a solution. Now, why would that prove that we can get an overall solution by repeatedly making the greedy choice? if making the first choice is safe in the sense that from that point there'll be a way to find a solution. How does that solve our problem? I mean, you can think about that. We can discuss that a little more in a bit later. Let me show you how it works. So let's M be the meeting with the earliest ending time. So there has to be at least one optimal solution. There could be more. There has to be at least one. Let's call it S. And suppose that S does not contain M. Well, some meeting in S, we'll call it M prime, has to have the earliest ending time that's in that set. So let's take that set that doesn't contain M. Let's remove M prime from it, and let's put M into it. I claim that this new set, S prime, is a valid meeting schedule. There'll be no conflicts. If S does not contain conflicts, S prime will not contain conflicts. So what's the argument there? So taking out M prime and putting in M will not cause any meeting conflicts. Yeah?
Because M has to end before M prime, right?
Okay, yeah, M has the earliest ending time overall. M prime is the earliest meeting time in S. So yeah, M has to end before M prime. Okay, so let's go from there. M ends before M prime, so why will taking out M prime and introducing M not cause a problem? Yeah?
Because it'll end before any of the other meetings start.
Yeah. So it's, by necessity, M prime ended before any other meeting in its schedule started. And M ends even earlier. So it's not going to conflict with those meetings either. So it's safe to remove M prime and put it in. Now you have a new optimal solution. It's just the same, it's optimal. How do we know it's optimal? We know it's a solution. How do you know S prime is an optimal solution? Yeah.
Because if X was an optimal solution, and we picked one with an even earlier time than that.
Yeah, well, S had some number of meetings, right? The most possible. S prime has the same number of meetings as S. No. So if S is optimal, S prime is optimal, because they contain the same number of meetings. So that's what this next point says. So what that tells us is that, well, what does that tell us about making your first choice be M? If your first choice is M, could you be in a situation that you're not going to be able to add more meetings and reach an optimal solution? We want to see that it's always safe to make the greedy choice, that we're not going to be stuck. So what does this S and S prime business have to do with that? Yeah.
It's just saying, like, if M is always safe to put in as the first one, you might as well always do it.
Okay.
Because it shortens the problem you have to solve.
But how do we know it's safe? Yeah.
I guess what this kind of tells us is that any valid solution can only be improved or, well, not changed by adding
Okay.
M instead of an M prime.
Okay. Or another way to put it is, there is an optimal solution that contains the greedy choice. What we showed is there could be lots of optimal solutions, but we just showed that if you find an optimal solution, if there's an optimal solution that does not contain the greedy choice, I just showed you how to transform it into an optimal solution that does contain the greedy choice. So that means that there's an optimal solution that contains the greedy choice. If we make the greedy choice first, then there's more things that's a good start. We're not blocking ourselves off from finding an optimal solution. And now we've reduced the problem to a smaller problem, and we just iterate. We found an optimal solution for what's left of the problem and add into that, and we've got a overall optimal solution. Okay, so this is an example of an optimization problem, and we're going to be looking at optimization problems the rest of the semester in various forms. And what they all have in common is a set of choices to make subject to constraints. In this case, we got to choose meetings. The choices are which meetings to use. and the constraint is they can't overlap. And the goal is to find a set of choices that are optimal according to some metric. In this case, we want the largest set of possible non-overlapping meetings. We are going to be interested for the next while with optimization problems that exhibit the optimal substructure property. And the definition is an optimization problem exhibits optimal substructure if every possible solution contains within it optimal solutions to each of its subproblems. Now, that's a mouthful, and let me explain what I mean. Let's suppose this is the optimal solution to the meeting problem. Right? Suppose that suppose we took this thing here, this meeting here, and we threw it out and we said the meeting is not available during this time. The room is not available during this time. And now I ask you, what's an optimal solution to the problem of scheduling meetings into a room that's available during this interval and during this interval? What would be the quick way to find the optimal solution to that problem? What's that? Well, how could we find the solution to that problem from this optimal solution? Yeah?
The only thing that needs to change is checking if there's a meeting that slots into that tiny spot.
Well, there wouldn't be, because it would have to end earlier than this one. It wouldn't be in the set. Yeah?
You just have to remove the conflicts.
Yeah, well, all we have to do is, if I told you that the room is only available during these times, where this gap is exactly linked to that minute, that meeting, what's the optimal solution to this problem down here? Just throw that away, and what's left is an optimal solution to the subproblem. That's the optimal substructure. This is one subproblem that you get by sort of making the room unavailable during that meeting. That subproblem's optimal solution is right here. It's part of the optimal solution. If we make that the room unavailable in the second meeting, that second slot, then the optimal solution to this subproblem is those three. So you don't have to go and recompute from scratch. Or in other words, think about how the reason this is important is, think about how the algorithm works. We choose this meeting first, right? That's the greedy choice. And then we solve a subproblem. What's the subproblem we're solving? Once we commit to putting this in our solution set, we solve a subproblem in a greedy fashion. What is the subproblem? Yeah?
Everything that comes after.
It's this right here. It's scheduling meetings into a room that's available during these times. So we need to have problems that can be solved that way. We solve the problem by, if we make the correct first choice, then if we find an optimal solution to what's left of the problem, then we'll have an overall solution to the original problem. That's what optimal substructure means. But there are lots of problems that exhibit optimal substructure. Let's look at some examples. So here's some possibilities here. This is the general form of the algorithm. You survey the choices and efficiently pick one. You eliminate the conflicting choices. You solve the reduced problem. You don't have to reconsider and backtrack later. And when you want to prove a greedy choice is correct, what you have to show, as long as you got optimal substructure, all you have to show is what we did. That the greedy choice is part of an optimal solution. That's really all you have to prove. Unfortunately, we can't solve all problems this way. So here's a variant. Maximize the amount of time the room is in use. Maximize the number of people who are able to attend meetings. Maximize the total value of the meeting scheduled. Those are examples, variants of the meeting problem for which there's no greedy algorithm anyone knows. Okay, here's some other problems. This is a classic one, the traveling salesman problem. It's an optimization problem. We want to find the shortest path. Imagine you have a weighted graph. You want to start at a given vertex, and find a path that visits every vertex once and then goes directly back to the start. A cycle that visits every vertex once. And you want the cheapest such path. That's an optimization problem. What would a greedy algorithm look like for that? Yeah?
Shortest path from start.
Well, one solution, one way to approach it would be to pick a path and see how long it is, and then back up and try a different path until you find the shortest path, the shortest cycle. That takes a long time because there are a lot of possible paths. But what would the structure of a greedy algorithm look like for this?
Is there a greedy algorithm
No.
for it?
Not, there's no known greedy algorithm, but if there were, what would it look like? Yeah.
So you could know the right first edge to go with, and then that's a sub-problem.
Yeah. So you pick a starting vertex, doesn't matter where you pick, because they're all sort of equivalent in that form. And somehow by magic, you pick the right edge to follow first. You make a greedy choice. Say, that one right there is the right one to go. So you go to another vertex. Now you got a sub-problem to solve. You make another greedy choice. Which of these is the right edge to use? You follow it. It'd be nice if there were such a greedy algorithm, but not only is there not one, there's not, it's very unlikely there is one. Okay, satisfiability. Suppose I give you a Boolean expression like x and not y. And I ask you, what value can I give to x and y to make this thing true, to make this expression true? We can solve that. X and not y. You make x true and you make y false, and it becomes true. But imagine you had, hundreds or thousands of variables, all, anded and ored and knotted together, and you had to find a way to make that thing true. Turns out that's an important problem. And it'd be nice if there was a way to point to a variable and say, yeah, that one needs to be true, and that one should be false, and that one should be true. There's no known algorithm, and very doubtful there is one. The shortest path problem, the general one where there are negative cycles. No known greedy algorithm, but of course we know Dijkstra's algorithm will solve a subclass of it. So there are lots of optimization problems you can't solve with greedy algorithms. Here's another classic one. It's called the knapsack problem. A thief has a knapsack, and so imagine you're the thief and you can carry away W pounds worth of stuff. And you go to a room and it contains a pile of item A's, a pile of item B's, a pile of item C's, and they each have a weight, each have a value. And you want to stuff your pack as full as you can, and your goal is to get as much value as you can from it. Which item should you take? Okay, so in this particular problem right here, well, I need to give you a particular problem. What if your knapsack can carry 10 pounds? Which items should you take to maximize the return? We should take an A, that's 13, and then probably a C, so that would give you $17 worth of stuff. Okay? What about if W was 12? A and B would give you 20, but I can do better than that. 3 B's would give you 21. What about 9? Two B's would give you, 2 B's would give you 14. I was about to say just a single A. So, does having done that give you any idea of what a greedy choice, how you would make this greedy choice? How would you look at the table and say, okay, it says the optimal substructure property because we can, if we could make a greedy choice, we could make the choice and that reduces the problem. Now our pack has less capacity, now we've got to solve a subproblem. But can you think of a way to make a greedy choice? Yeah?
Prioritize B the most, and then
Prioritize what the most?
item B. How many times
Okay.
do you store item B?
All right, so why are we prioritizing item B? What is it about it that makes it? So you're basically saying, if you can take an item B, do it. Right?
Yeah, up until
Okay, but I got a counterexample for you. What's the counterexample? Right. It doesn't work here. So in this situation, B can't be the greedy choice. So a greedy choice would look at it and say something like, which one has the most bang for your buck? I mean, which is the most valuable per pound? A. Okay? So we could try that. We could say, just look at it and figure out 13/7 is more than 7/4, and that's more than 4/3. So take as many A's as you can, and then try to fill in the pack with what's left. First you steal A's, and then you steal the B's, then you steal the C's. So A's are most valuable. But what's the counterexample?
2.
Both of these are counterexamples. In neither case here does it work. Think of any other greedy choice ideas. Yeah.
Can we compare weight to some kind of factor that allows us to determine how much space it takes up in terms of how many other items we can use?
Well, space isn't a consideration. The capacity of the knapsack is just based on weight. All we got is weight and value to work with. Yeah?
Did you figure out which item has the highest weight to value ratio?
Well, that's what we were just saying. A has the highest weight to value ratio. Or
Right. But
highest value to weight ratio.
But normalized for when the weight is 1. So and then sort that list and then pick the densest one that you have a common factor with.
Okay, so that's a suggestion. I won't try to construct a counterexample right now, but I'm pretty sure I could. You get your question back there.
Could you take the knapsack weight and mod it to the item weight to see how much space you have?
Okay, so we're taking the knapsack weight and modding it with the value, with the weight of the items. And how do we use that to make a greedy choice? I mean, it's a good idea. Just you need to pin down some details. I'll let you think about it. Yeah?
Should you do a blended algorithm and do a comparison, like you said, when you mod weight to the knapsack weight,
Mm-hmm.
and then do a comparison, for example, when it is not, when you can't use the most of whatever it would be in the comparison. I can't think of it in my head right now.
Right. So I think the idea of both these suggestions, maybe all three, is we don't want to, maybe we don't take an item A if it would. But the problem of taking an item A in this situation is it leaves some difficult to use capacity in the pack. Yeah?
I have the same question. Is there a greedy algorithm?
Okay. There's no greedy algorithm. And you would become very famous if you found a greedy algorithm that solved any of these problems, these last three problems. The knapsack problem, traveling salesman problem, or the SAT problem.
Slide to the true false one.
Say again?
Can we go back a slide to the true false one?
Yeah. How do you go backspace?
I was just thinking, couldn't we use the same majority algorithm that we use for galaxy quest? You just you treat the trues and falses as ones and zeros, and then you find the majority. And if you got the majority was true, then to make it false, you just have to match it with the difference of falses.
Yeah. That'd be a nice thing to try, but again, people would be very surprised if it worked. Yeah.
Isn't the fundamental problem that each local choice is tied to every other local choice?
With this SAT problem here?
Yeah, well, with any of these.
Yeah, the problem with SAT is a variable can occur here, it can occur way over here, in different contexts. It can be negated here and not negated there. And yeah, when you do this problem here, the first choice you make determines how much capacity is left in the knapsack, and it's just hard to see. And no one has ever found a way to make that choice perfectly every time. Yeah.
So, according to all the algorithms that we're doing, what necessarily is what makes a greedy algorithm defined as a greedy algorithm?
Yeah, he's asking how can you look at something and tell is there a greedy algorithm for it? And I don't know a better answer to that than you try to find a greedy choice and see if it works. Okay? So it's not always obvious that a problem can be solved in a greedy fashion. Yeah.
This may not be greedy, but something
want the one with the highest price to weight ratio of the ones that factor, like of the weights that factor. So since none of them in the first case do, you just take the most A, but since 3 and 4 do for 2, you would take B because it has a higher ratio.
Yeah, I mean, that's a greedy choice, but again, it's almost certainly not going to work. Just because, good reasons to think that there's not going to be a greedy choice that works. Yeah?
Isn't there a way to look at problems like this from a point of view that makes them similar enough to other problems that you can categorize them?
Well, a lot of times, yeah, you can look at a problem and see it similar to some other problem that has a greedy solution. And
So
know that-
like this problem is NP hard.
Yes.
Isn't there some approach you can take to saying this is, if you look at the steps it would take to solve this, it's the same as this other problem, therefore it's NP hard?
Yeah, that's a topic for another day.
Okay.
Okay. Here's a very similar problem to the knapsack problem. Making change. So suppose you buy something at the store and it costs 79 cents and you give $1, how do they typically make change? What are they trying to optimize when they make change, assuming they have a lot of each coin? Yeah?
Usually you want to go with the higher value coins first and then bring it down.
Okay. So they want to give you as many quarters as possible, and then as many dimes as possible, and as many nickels, and then as many pennies. So there's a way they're trying to optimize. Another way to look at that is what they're doing is they are optimizing the number of coins they give back to you. Let's think of it that way. So when you give change, you typically want to give back the minimum number of coins possible. Now, is there a greedy algorithm for this? Okay. And I think we just discussed it. The algorithm is give back quarters until you can't, and then give back dimes until you can't, and give back nickels until you can't, and then pennies. Now, it's not clear that people think that way when they give change. But that's the way to solve the problem. So if I got to make 30 cents of change, I take a quarter, because my greedy choice is the most valuable coin possible. So I pick the quarter, and that leaves me the problem of making change for 5 cents. So I'll give a quarter and a nickel. If I got to make 12 cents, the biggest coin I can use is a dime. That gets me down to 2 cents. 55, I don't have half dollars on here. 2 quarters and a nickel. So is making change somehow simpler than the knapsack problem? Well, making change with American money is simpler than the knapsack problem. Now, sometimes they talk about getting rid of nickels. They talk about getting rid of pennies too. But suppose we got rid of nickels. What happens with making change now? Does this greedy algorithm work if we don't have nickels?
Yeah, you just like this.
Can you think of a counterexample where if you make change like I just described, you give all the quarters you can, then all the dimes and all the pennies. Yeah?
Example 3.
Example 3, 55 cents. Well, what would happen there? You'd give 2 quarters and 5 pennies for 7 coins. What's a better way?
Quarter and 3 dimes.
Quarter and 3 dimes. Or another example would be making change for 30 cents. Okay? The greedy algorithm would give you a quarter and 5 pennies. The better solution is 3 dimes. Okay? So, in general, the change problem is also hard. It doesn't have a greedy solution. It just depends on the denomination. It just so happens that our denominations have that property. The greedy algorithm, I guess that's why people can make change, or could make change before there were computers telling them what to do. So that's our introduction to greedy algorithms. We will continue on in 12 days. So have a good spring break.